All right, here's an additional example for section 7.5. We're doing an additional pumping problem where our radius varies as the y value, as the height in our container changes. The example we did in class, the radius was constant in the cylinder, so we can just each disc, each little slab of liquid that we're thinking about, the cross-sectional area, the volume of each little disc was the same. In the sphere, the volume of the little discs are going to change as the height in the spherical container changes. So here's our setup. We have a spherical tank. And it has an 8-foot radius. It's half full of oil. And the oil weighs 50 pounds per cubic foot. We want to find the work required to pump the oil out through the top. So let's draw pictures, make a little sketch, define our coordinate system, and draw our representative little layer of the oil. So here's my spherical tank, and I'm going to set my coordinate axes. I'm going to have the y-axis go right through the center, and my x-axis go out this way. And the oil, it's half full. So here's the level of the oil. And the height, the radius of our tank is 8 feet. So from the top to the bottom is going to be 16 feet. If I put a little representative layer of liquid here, so here's my little layer of liquid in the tank. The height of this representative layer is going to be y. The thickness is, I'm going to call it dy. You can call it delta y if you want. So the thickness is dy, and the distance that this little layer of oil has to be pumped to go out the top is over here. This distance is 16 minus y. So in order to pump this out the top, we have to pump it through a distance of 16 minus y feet. So the thickness of the layer of oil is dy, and the radius of this particular layer of oil is x. and the force required to lift the oil, lift this little layer of oil, is its weight. So I'm going to call that force, that increment of force that is required to lift that layer of oil out the top, dF. So that's going to be 50 pounds per cubic foot times the volume of the disk. The volume of the disk is going to be pi times x squared. X is the radius. The radius of that disk is x. Let me label this. If I drop this down, this distance is x. From here to here. So x is the radius of this particular disk. So pi x squared, and the thickness is dy. So that little circular disk has a weight of 50 pounds per cubic foot times pi x squared dy. Now we're going to integrate with respect to y. So we're integrating as we change the depth in our tank. So we're integrating with respect to y. So our radius varies as we move inside the tank. We need to come up with an expression for the radius of our disk in terms of y. So I need to find that expression. So at the surface of the oil, here right in the center, it's half full of oil. At the surface, we have a circle. Its radius is 8. And the center is at 0.8. So we have a radius of 8. Our center is at coordinate 0.8. And I'm going to say that because we're here in the center of the sphere, it's symmetrical no matter how we turn that circle that we're looking at. The situation is symmetrical, so we can write a relationship between x and y that's going to hold over the entire sphere. So we're going to write an equation for the circle. So x squared plus y minus 8 equals 64. So this is the equation of the circle, and I just need to get an expression for x in terms of y. I can rearrange this, and I get x squared equals 16y minus y squared. So I'm just going to expand this and subtract everything from 64, and I get x squared equals 16y minus y squared. And my radius is squared here, so if I just leave this in terms of x squared, I can just substitute it right in here. So here's my expression for x in terms of y. So this is going to hold throughout this sphere. The distance, we said the disk of liquid moves is 16 minus y. So our small increment of work, dW, is going to be dF, our force, times 16 minus y. So our expression for our force is 50 pi times x squared, which is 16y minus y squared, times the distance that we pump it, that little disk, and we have our factor of dy for for our weight, for the thickness of our little representative disk of liquid. And if I expand this, I end up with 50 pi times 256 y minus 32y squared plus y cubed dy. And since the tank is half full, I'm going to integrate from y equals 0 to y equals 8 to get the work necessary to pump that liquid. So my work is going to be the integral from 0 to 8 of 50 pi times 256y minus 32 y squared plus y to the third dy. So we're just integrating this polynomial, an easy evaluation. And when I evaluate this, I get that this is approximately equal to 589, 782 foot-pounds. So the trick or the challenge or the additional piece of information that we had here is we had to come up with some expression for x in terms of y. And because our tank was half full, we could write this equation of the circle to come up with an expression of x in terms of y. We get the radius of these little representative layers of oil as a function of the height above the bottom of the tank.